So Atena Akbari is a postdoc in Ravi Menon's lab in London, Ontario. As we heard already, they have a very cool head system, head gradient 70 system, which is back at field since a few weeks, I guess. Atena is a user of layer-fMRI VASO, previously also in Australia, in Queensland, with kind of classical Magnetom 70 from Siemens under Markus Barth and Saskia Bollmann, and now I'm continuing doing layer-fMRI VASO in London. Today, she will talk about the talk that is coming up for ISOMREM, namely doing simultaneously laminar and columnar VASO fMRI. Yeah. Please share your screen. Atena, I think you're still muted.
Okay. Hello again, everyone, and good morning to you all. And first of all, thank you so much for giving me this opportunity to talk about my work with you. As Ravi mentioned, because we are going to submit this work soon, I am super happy and excited to share the result before submission with you guys. So any feedback is highly appreciated in any of those results. So thank you so much in advance. Okay, so let me share my screen. Okay. I am going to present our work on, let me minimize this so I can see the slides better. Yeah, I'm going to present our recent result on depth-dependent examination of ocular dominance columns with BOSE and VASO fMRI at 70. And because I am presenting to a group of experts, I try to keep the introduction very short, and because I really wanted to discuss the results more with you guys and receive feedback on them. And also, please feel free to stop me throughout the talk if you have any questions. Okay. So, as you know, the ocular dominance columns are a group of neurons that are located in the primary visual cortex, in which they respond preferentially to the input of one eye or another. And this thalamocortical input that we are talking about, as you know, arrives mainly from LGN to the middle layers of the primary visual cortex. And also, to some extent, this input arrives in deep or infragranular cortical layers. Here you are looking at this famous picture of a postmortem human brain. So this person lost an eye around, I guess, 10 years before her death. And you are here looking at this fingerprint-like pattern of ocular dominance columns that have been acquired using the cytochrome oxidase staining. And these dark patterns are correspond to the surviving eye because they show a recent metabolic activity. And the pattern in between are correspond to the last eye. So the ocular dominance columns in vivo first image using gradient echo bold contrast back in 1997 by Ravi and colleagues. And you are looking at this columnar pattern shown in orange and purple that are correspond to the right eye and left eye simulation. But as we all know, gradient echo contrast spatial specificity is kind of poor because of this draining vein effect. So a couple of years later, Jakub and colleagues tried honey-spin echo that actually provides us with a higher or better signal spatial specificity compared to gradient echo to reveal these fine scale structures in the human brain. And if you compare these two maps, you can see that with the spin echo, because of the reduced effect of those draining veins, we can see this pattern a bit more well-defined and clearer. And then also in back in 2022, this is this nice work by Daniel Henlett and colleagues, and I guess Renzo was also one of the authors in this work, in which they showed the feasibility of the VASO fMRI in mapping this ocular dominance column in addition to spin echo and gradient echo. Then here, back here in CFMM, the whole point and aim of the study that we did, we wanted to do some sort of comparison between the bold and VASO contrast in terms of the signal sensitivity and signal spatial specificity in imaging the laminar columnar structures in addition to the laminar structures that have previously been shown in human V1. The sequence that we used is the DZNE sequence. As you are here looking at an example of our imaging slice on one participant here that has been centered on calcarine sulcus where the ODCs are actually located. In each imaging, 5 people participated in this study. And at each imaging session, we acquired 5 functional runs with 200 volumes for each contrast. Our resolution was 0.7 millimeter ISO, and the TR was around 3.3 seconds. And for the visual stimulation, we used a flickering checkerboard that was sequentially presented to both eyes, right eye and left eye. Let me get my pointer. Interleaved with this gray screen as a control condition. We use this MR-compatible goggle to deliver the stimulus to binocularly and monocularly. And also we use this occipital coil that Kyle Gilbert here at CFMM built specifically for this type of studies, which is really advantageous because it allows us to mount this directly over the participant's eye. Also, it's a little bit, because there is no obstruction, visual obstruction, it's a little bit stressful for the participants. Then the analysis.
Sorry, if I might ask one more, like VASO-specific hardware setup question. Then, like I know you in London, you use PTX like regularly, and so based on the localizer, it looks like you have a kind of this like visual cortex-based receive coil, but I'm also wondering which kind of transmit coil you use. Like for VASO, you need to have kind of the inversion for all the blood supply of the feeding arteries which come into the circle of Willis. So did you have to kind of, what kind of transmit coil do you use? Did you have to kind of adjust the PTX shim for the inversion pulse and the excitation pulse separately, or what kind of setup did you have like used there?
There was a specific setup.
Yeah, so it is PTX. It's an 8-channel PTX coil that is built into the coil that Atena has in the bottom right of the slide. So that the PTX coil covers more of the volume than the occipital coil. So this is a coil built specifically to do, cerebellum and occipital parietal studies, of which we do many in our lab for other reasons. So there are 32 receive coils, basically over, V1, V2, V3, V4, maybe extending into MT. And the PTX goes all the way around, and we shim on the volume of interest. PTX shim on whatever defined volume of interest we want. And as you can see, even from the, I don't know whether the Scout was shimmed or not, but you can see that the brainstem circle of Willis and everything is excited quite well, even though the coil sensitivity, receive coil sensitivity, is defined at the back of the brain. So yes, we think we're getting the inversion in the circle of Willis completely.
Cool, thanks.
Yeah, okay. And yeah, about the pipeline, it was just the basic fMRI analysis pipeline plus the layer analysis pipeline that Renzo has published in his blogs. So generally it was first the contrast separation, bold and VASO contrast separation, and then we applied Nordic to reduce the thermal noise contamination. And then the motion correction, bold correction, than getting the T1-like EPI image out of the mean image of bold and VASO. This is that image to do this, to draw the ROI and do the laminar analysis. I also did a bit of a smoothing with the LN-grad smooth that does actually the smoothing within these structures that share similar anatomical features. Then the layer plots and columnar plots that I will explain more in the upcoming slides. So first, let's take a look.
Atena?
Yeah.
Just a quick question. I was curious, did you apply Nordic to each of the contrasts individually, or were you doing it all at once?
No, separate.
Okay.
Yeah.
Cool. Thank you.
And then first, let's take a look at the activation maps correspond to both eyes, right eye and left eye, for each of the contrasts. So as expected, both signal sensitivity was much higher compared to VASO, as we have seen in previous studies as well. But on the other hand, the signal spatial specificity of VASO was much higher. You see that the activated voxels in VASO are more confined within the gray matter, but in bold are kind of spread all over the cortex. And if you look at the laminar profiles for each of these contrasts, again, as we expected for gradient echo bold contrast, we see this steadiest increase towards the cortical surface. Here you are looking at the laminar plots for both eye stimulation. This is for right eye and this is for the left eye stimulation. And I should mention that all my participants were right eye dominated. So in this plot and the following plots, the response of the right eye is greater than the response to the left eye for all of them. But for VASO, what we expected again was having this maximum signal change kind of in the middle layers of the cortex because of the absence of the signal from those draining veins. And also as a reference, here I have plotted the T1 intensity image plot as a reference to kind of show the location of the approximate location of this drug of Ganari and layer 4.
And this T1 is from like the EPI T1, is it?
Yes.
Oh, it's beautiful. Like how you see the kind of the toe before it goes down. This was not 0.8, right? Could you remind me? It was 0.7 millimeter. What was the resolution again?
The T1 is 0.75. Our functional was 0.7.
Okay, so the T1 image intensity that you plot here is 0.7. Okay, cool. Thanks.
And yeah. Okay. Here you are looking at the monocular column responses to the stimulation of the same eye and the opposite eye. So for example, let's consider the first one. Here is a response of the right eye dominated columns to the right eye stimulation. And this is the response of those columns to the left eye or opposite eye stimulation. This is for right eye and this is for the left eye. So the color has been chosen to kind of be easy for the to identify. So red stands for right, lavender stands for left eye. So for bold, as you see, the amplitude and trend of the responses are very similar. And this kind of shows this large gradient echo spread function, cortical spread function, and also this large overlap that exists between the neighboring columns that makes it difficult with gradient echo to kind of differentiate between the columns. But if you look at the VASO plots, you see that the response of the unstimulated eye, these dotted lines, are much smaller compared to the response of the stimulated eye. And again, this is probably due to this to the absence of these large veins. And because here with VASO, we are detecting the tissue signal change around microvessel, so it makes us a bit easier to differentiate between the columns, or it makes this ocular segregation across the adjacent columns a bit easier for us.
I have a quick question.
Yes.
Do you believe these kind of two humps here, like there's maybe a trough in the middle, and a peak, a kind of deep layer 4, and then a superficial layer, or do you think this is kind of one hump?
I love to believe that this double peak pattern is reliable, and I also talk about it a bit in the next slide. Yeah. Renzo, you had a question, or I should
Yes,
move on to the next
please.
one?
I was maybe you said it, but I was wondering if you could remind me of how you selected the columns.
Oh, yeah, sorry. So I created this binary mask with the threshold of 3.1 that's corresponded to significance level of
And
PS.
that was a mask that was not a difference mask of left versus right.
No. It was not a difference mask. No, a mask for right eye dominated columns and then a mask for left eye dominated columns.
There might be overlap between them a bit.
Overlap between these two, not really. Based on for bold, yes, but
Okay.
for VASO, I don't think so. Yeah.
Thanks. Yeah.
So you used just a quick question then. So you used the VASO map to segment the columns essentially, to pull out. I mean, it wasn't bold for, it was the VASO generated column information that then used across bold.
That's a great question. It could be a great approach, but actually no, I just defined this threshold and apply it to the bold separately, and then apply it to VASO separately, and then those masks are getting multiplied separately with their corresponding T maps. But yeah, that could also be another approach.
Because you might get better differentiation if you use the VASO and the bold. And it might possibly.
Yeah, exactly. Okay. Then next, here this plot actually shows the response of the plots that you're actually seeing here. The response of these two, these two, these two, and these two. And again, very interesting result out of this one. And I also like to know what you guys think about it. So for bold, again, it's kind of makes sense that differentiating between these responses or this ocular segregation is easier at deep cortical layers where you have the smaller number of these intracortical veins. And then it degrades or reaches to a value we call 1 as the cortical surface is reached, because here we have greater amount of overlap between the signal from adjacent columns. We have the veins have greater diameters, and also the number of these veins are also higher at that depth. With VASO, we got this nice, beautiful a double peak pattern at superficial and deep cortical layers. And our interpretation of this result was that it kind of might refer to that stronger horizontal connections that we have seen from animal studies in superficial and deep cortical layers. This might kind of correspond to those patterns that we have seen from animal studies. And in the next one, this is my favorite plot. I hope that my interpretation makes sense for this one. Here we have investigated the response of monocular columns to a binocular viewing. So basically the columnar mask, the columns that right eye dominated columns and left eye dominated columns separately, their response to a binocular stimulation. Again, for both, the response kind of makes sense because when both eyes are receiving inputs, but I am only investigating the response of, for example, right eye dominated columns, red in here, to that binocular stimulation. With bold, I expect to see a big overlap between the adjacent columns. And then, yes, the binocular stimulation, the response should be greater than the monocular one. But for VASO, interestingly, I see a reduction in the response of these monocular columns when the stimulus is presented to both eyes. And this reduction can be seen only in lower parts of the layer 4 and also in deep cortical layers. Then I was looking in the literature to see if any study has mentioned such effects before. And I found this study back in 2019, in which they showed that the monocular neurons response to a binocular stimulation is suppressed. So the more a neuron is monocular, the more suppressed their response is during a binocular stimulation. And these monocular neurons, as I showed in the first slide, and what we know from these ex vivo studies, that they are mainly located in middle cortical layers and also to some extent into the deep cortical layers, especially if we believe this correspondence of layer 4C, then it kind of makes sense. So I was kind of excited about this plot to see that this binocular modulation can be seen with the VASO contrast. If it's true, if it's a right interpretation for this result, then this is another beautiful application of the VASO for that shows it's very promising for this type of cognitive questions in the brain. And yeah, so
quick question, just before you summarize. So just once again, what are the maps at the bottom again? What's the contrast for the, those little rectangles? I mean, is it looks
here?
like, yeah.
Oh, this is the cortical layer thickness and boundaries from macaque's brain for the visual cortex.
Oh, okay.
I just put it here as a reference and how I kind of considered this layer boundaries and thicknesses across the ROI.
Huh, okay.
Yeah.
So in humans, we might expect that layer 2, 3 are slightly thicker, right? And kind of shifting it or scaling it down. Or is that established?
Yeah.
Okay.
Layer 2, 3 thicker than this?
And that, I mean, in humans, like in humans, cortex is slightly thicker, and visual cortex is mostly the layer 2, 3 that are. So
this one is for 2 millimeter, I guess. 1.6 to 2 millimeter is the thickness in macaques, and for human it's 2.5 millimeter. But again, based on the T1 plots that I had, and just this one, I don't know. I thought maybe that's the approximate location.
Yeah, I mean, certainly the boundaries are fuzzy in the absence of human histology, but yeah, Renzo's right, and I think Atena mentioned it, that the horizontal connections in layers 2 and 3 are a little bit thicker in humans than macaques, but not a lot. So maybe that 3-4A boundary moves around a little, but it's not clear where the boundary is and where the surface is and how exactly you map macaque histology to humans. So it's approximate.
It's also not so trivial to know the kind of CSF gray matter or gray matter white matter border at these kind of MRI data in humans. Also, yeah, it's always a bit kind of fuzzy. Yeah.
Yes, I mean, a couple of 100 microns either way, right? For sure.
I was curious about your interpretation here of having neuronal suppression in the monocular case, or the binocular case in monocular neurons.
Yeah.
If that is the interpretation, wouldn't you also expect to kind of see some kind of activity associated with the inhibitory circuit? In which case, would you think that layer 2, 3 should have an increased response in order to decrease the responses of deep neurons? Or how do you kind of balance those two things, the suppression and the neurons that are using energy to suppress?
Yeah, that is also could be added to this interpretation. But I don't know, based on what I have read so far, they just mentioned that they have seen this type of suppression in monocular columns. And then and then again, this study that actually referenced this showed that, okay, so far we have believed that this layer 4 is the location of these monocular neurons, but they also proposed a new circuit model that these neurons can also be found in layer 6, and then the suppression also kind of go down to the cortical layers. But about the superficial layer, honestly, I don't have any comments. I don't know.
Well, one thing that's interesting is that certainly the inhibitory neurons, say coming from the higher layers into the deeper layers, if those are GABAergic, for example, or inhibitory in general, those inhibitory synapses are always closer to the cell body and are actually metabolically much more efficient than excitatory synapses. So it doesn't actually take much of an increase in drive, and maybe it's below the threshold for us to detect to actually cause inhibition because of the efficiency of inhibitory synapses.
Yeah, that's a really good point. I also had the thought process that perhaps the inhibitory response that you would see is not in those columns, but the adjacent columns,
right,
etc. So like there are a lot of possible reasons that you could see data like these, but it's really cool to have this starting point.
Yeah, I mean, we could stick a Utah array into a macaque and do these exact same experiments and see. Nobody's actually done that because everybody thinks V1 is boring these days, but they're all in prefrontal cortex and LIP and FEF and places like that. But there's still a lot we don't know about V1.
Yeah, okay.
So one other random thought, sorry, given the context of this, is I think I saw from Sanji's work that, right, because the inhibitory response is less metabolically active, then maybe the bold response would be correspondingly higher for inhibitory signals than in the excitatory. So it might be interesting to compare the bold to VASO, since VASO shouldn't be affected by that because you're not affecting the oxygenation. It still might drive the hemodynamic response, but it might be interesting to compare VASO with bold with inhibitory and maybe to further stratify things potentially. So just a thought.
Yeah, definitely.
Yeah, I mean, you could somehow try to deconvolve CMRO2 from flow and blood volume. I think you'd have to really do an ASL experiment along at the same resolution, so that will be interesting.
Yeah.
We're building a new version of this coil actually, which is even smaller. So it has 32 channels, but it is truly a V1 only coil. It doesn't even go into the cerebellum and parietal areas. So we're thinking that may double the SNR yet again. And then we're looking at a cryogenic version of that coil, and I have no prediction as to how much that will improve, if at all, but that's a major engineering challenge, as you can guess.
Yeah, I always thought that cryogenic coils, if it's loaded, then it won't make a difference as much, but it could. Yeah.
Yeah, but that's 70, you're kind of still borderline there. There's contributions from both, and of course, anything you can reduce coil noise and preamp noise still helps. So the other thing is the cryogenic coil we're considering, we're going to build it ourselves, is nitrogen cooled. It's not helium cooled. So you only get about 70% of the benefit of a helium cooled coil, but you get only 5% of the headaches compared to a helium cooled coil. So yeah, a lot of questions as to whether cryogenic coils are useful at 70 in humans or not, but we'll see.
Worth trying.
Yeah,
So one more quick question. So how many subjects do you have for this experiment?
5 participants.
Also, can you find all the this double peak pattern from all the subject, or only have some like very champion subject?
Sorry, could you repeat your question?
Oh, so I just want to confirm whether you can find the double peak pattern from all the subjects.
Yes, yes, it was visible in all of them. Yes, the double peak pattern. Yeah.
So I also found you have multiple slices for this data set. So what about the size of the column mask? Use only one slice, or all the slice you arrange all the column from each subject?
I did this in a couple of slices. The number of slices might have been different for each participant, but it was definitely more than one. So maybe 3 slices, 4 slices. Yeah, usually in the middle that I had a nice contrast to draw the ROI. Yeah, it was more than one.
Okay, thank you.
Thank you. Okay, so in general, this study shows that the ocular segregation is better achieved with VASO, and it's a bit clearer at superficial and deep cortical layers. Also, it showed that the VASO remained specific to monocular columns response even when both eyes were receiving inputs. And the binocular modulation of monocular columns, the last figure actually that I showed here, this type of modulation might possibly be examined with VASO. And at the end, gradient echo bold signal is apparently degraded as in terms of a spatial specificity in both columnar and laminar direction. In the laminar direction, due to this veins that actually run perpendicular to the surface and drain the blood from white matter to CSF, and across the columns, probably in addition to those in addition to those intracortical veins, there is also veins that run parallel to the cortical surface that degrade the signal across adjacent and neighboring columns. So that's it. Thank you for listening. Share.
Thanks a lot. Maybe I have a question. So in your previous work, you developed these kind of models, and maybe this question follows up with Peter's comment about kind of separating the vascular from the CMR2 response. But so you already do have kind of a vascular response, and you do have kind of a vascular plus CMR2 response from the bold. Now also on like in your lab, you have all this expertise in kind of this like phase regression, right? That I believe still that some of the like columnar unspecificity that you see in bold might be not really due to just draining along the tangential veins in the cortex, but also just blooming effect from the veins that sit on top. Mm-hmm. And you could kind of get rid of them because they are like huge and it's just the phase field. So have you considered kind of combining those components like to tease out more information, in the sense that now it seems that kind of VASO is better in the sense of separating and profiles and better differentiating peak features, but at the end kind of VASO is noisy, right? So you kind of it always makes sense to harvest as much as you can to pull out as much convincing information to and kind of tweak your conclusions based on that. Is this something you're working on, like, or where is the kind of vascular modeling work continuing?
Well, vascular model is on hold for now, but with the phase regression, I have some results of Brett Liam to actually show you. He did this phase regression.
Yeah, so Brett is a master's student of mine who's just finishing up, and he and Atena did a lot of work with phase regression in a separate set of experiments.
Yes. So this is the laminar plots that Brett has acquired from the native magnitude data before actually phase regression and then after this phase regression. So again, the green is the both eyes, red is the right eye, and blue is the left eye. And this is the laminar response. So you can see that after correcting for the phase around those large intracortical veins, we have this nice drop of the signal at the cortical surface. So it's
Are
kind
you sharing your screen?
sorry?
Are you sharing your screen?
Yes, you cannot see it?
Yeah.
I can see.
Oh, I can see it.
Oh, really? I must have lost it. Oh, here we go. Now I can see it. Sorry.
Are these the same bold data as in the previous slides?
No, this is a separate data set. This data has been acquired with a multi-band API sequence with 0.8 millimeter isotropic resolution and TR 1 second. And the participant were completely different. So in this, after this is the laminar responses for monocular and binocular responses. And you see this nice drop of the signal around the cortical surface and see kind of this maximum signal change in upper layers of the layer 4 probably. And then he also, these are the monocular column response to the same and opposite eye. So we can see that the phase regression actually cannot kind of improve the ocular segregation. So you see this solid red line is a response of the right eye to right eye dominated columns to right eye stimulation, and the dotted red is the response of the right eye dominated columns to left eye stimulation. So it does kind of help with removing the unwanted signal around those large vessels, but not actually very effective in improving this, dissociating the signal across adjacent columns. So that overlap still exists across these columns. And this is the monocular column response to binocular stimulation. Again, for the native gradient echo magnitude signal, we see that the monocular column response to binocular stimulation is greater. It's the same thing that I actually had with my gradient echo. That's exactly what we expected. But again, phase regression does not improve. It's better, obviously, but not that much improvements with these phase regression. And then that's why we thought that this phase regression probably is helpful for correcting the vein effect around those intracortical large veins, but probably not for the horizontal veins that actually run parallel to the cortical surface.
Yeah, because, in our previous and even current estimates, I think you made an estimate too, Atena, but it's phase regression is just not particularly sensitive to vessels that are probably somewhere in the neighborhood of 200 microns and smaller. Yeah. So, they will suppress a lot of the cortical surface stuff, but a lot of the horizontal veins or venules in the cortex are 50 to 100 microns, and they give still a lot of bold signal, but the phase is just it's not strong enough. It's a noisier signal after all, to be able to do much suppression there. So phase might be good for laminar, but it's certainly not good for columnar. And even the peak is a little different. It's a little bit higher in the cortex, as she's shown, than VASO, which is this kind of nice plateau in the sort of middle third.
And you totally missed the 2 peaks, which I think is
important. And you totally missed the 2 peaks, yes. Although so we have seen that in previous studies, and as have other people. And the difference is our early work was actually done with flash and actually much higher in-plane spatial resolution. It was I think it was 500 or 550 microns, while as Brett's data that Atena is showing here is 800 microns. And that's nominal before you include T2 star blurring due to the EPI acquisition. So, you know, it's possible that we're just blurring it out. With the CMRR multiband sequence that we used for this, and even with we do everything with a head gradient coil, which is much higher performance than the body coils. We still can't reliably get good quality EPI below 800 microns for single shot. So you have to go to segmented acquisition, or we're looking at some compressed sensing spiral approaches. So I think we can reserve judgment on whether bold completely sucks or only partially sucks until we can improve the resolution.
Right.
And then we'll see.
But seeing those two peaks seems like a reasonable benchmark.
Yes, for sure. Because that corresponds with reality from what we know.
Absolutely. Awesome.
Sri?
Hi, Atena. Thanks for sharing your research. I had a question in regards to if you feel or you have the sense that these results you shared might have implication on explaining the mechanism of ocular dominance. To flesh that out a little bit, if I remember correctly from my long past neuroanatomy classes, I think the dogma is that ocular dominance is largely created by greater input from one eye. And if that were the sole mechanism, then wouldn't we expect to find there to be in right eye dominant people this this difference in response for the right dominant regions only in the middle layer, the input layer, and then they sort of come together, the left and right come together in superficial and deep layers. But if I'm seeing what you're seeing, it's sort of consistently different across the entire cortical widths, suggesting that there's differences that might be maintained even in input layers between the right and eye. So that was just sort of my thoughts when I was looking at your results.
That's actually a great question, Sharif. We've just been discussing this, but you know, one of the benefits of being old is I know the old literature, and so of course, the interesting thing about being right eye dominant or having an enucleated eye is when you're right eye dominant, your right eye columns are actually physically larger. So and that is preserved throughout the whole column. And so it's not just an input tuning effect. There is a physical size difference. And that, I mean, this has been known. John Horton's work has shown this in cytochrome oxidase staining. Electrophysiology work has shown this going back to Hubel and Wiesel, actually, although they didn't have the benefit of lots of electrodes. You know, when you move into the far enough visual field, you know, peripheral visual field, it's one big column because you only have input from one eye. And so that's one single giant column. Nobody's ever studied this with fMRI because you can never get the field of view large enough. Our field of view is 40 degrees, which is huge by fMRI standards. But it's still not enough to look at that, you know, sort of peripheral, monocularly only innervated areas of the cortex.
You must have the blind spot.
You do have the blind spot, but you need to do eye tracking to really to ensure that the person is staring at something, because if they're moving around by even a few degrees, you lose it.
Yeah. If I remember the Horton paper, the columns get larger as you get closer to the blind spot.
That is correct. Yes.
Yeah, it'd be nice to quantify that if you could, if you have that in your data.
Yeah, I think we can't at this resolution because, you know, Atena used 700 microns and Brett used 800 microns. These are of the order of the column size. I mean, they're almost exactly matched to the column sizes. So that's just not good enough to do the kinds of things you're talking about.
Right.
I think, you need to double the resolution at least before you can start making those kinds of comparisons.
Or at least 0.5.
Yeah, but so you can see where we're going with this, with all the various RF coil
Right.
advances that we're trying to make.
And the other thing I wondered about is, do you see the column stop at the V1, V2 boundary?
Sorry, again?
So if you go to the V1, V2 boundary, you should see the columns disappear.
Yeah.
So that would be a nice test that you're actually measuring columns and not just, some selection bias or something. If you do the same analysis just over the fence.
So one other random thought that I had looking at this, it sort of spurred me looking at the suppression effects or the potentially inhibition effects is this old paper by Ogawa looking at the temporal delay between with, I think he did it in mouse, but he also did it in visual cortex. At like 200 milliseconds was optimal suppression of like the feedback. So basically you had visual simulation, and if the 200 milliseconds, which is like 10 hertz, that optimally suppressed the corresponding activation. But if you modulated that frequency or the time between, then the suppression varied. It might be interesting to play some games in that domain with this, either left, right eye or something like that. That you might see a nice clean modulation of this suppression essentially. So.
Yeah, for sure. There's actually a really interesting paper that just posted on bioRxiv a few days ago, which looks at binocular rivalry. And I was just flying out here, so I didn't have a chance to read it. Atena has looked at it in a little bit more detail, so she could comment more on it. I'm not sure they look at columns. Do they look at columns, or they just look at cortical responses in layers?
They actually mapped these ocular dominance columns with 3 different experiments. And one thing about this binocular rivalry that was interesting to me from that paper was that they showed this binocular rivalry is strongest at superficial layers. And I was thinking that we didn't study binocular rivalry, but the concept is kind of similar to the ocular segregation, because in the binocular rivalry, you are presenting different stimulus to each eye. So you want to be able to dissociate between these responses. And I thought that is kind of similar to the ocular segregation that we studied. And we showed that it is stronger at superficial and also in deep cortical layers. And if I'm not mistaken, they only reported it at the superficial layers. They have removed these high intensity voxels that correspond to the bold activation due to the veins at the surface. But I was thinking that the bold propagation of the signal across the columns will also manifest in deep cortical layers. So maybe that's why they couldn't see it in deep layers as well of the superficial. I'm not sure. But I thought it's kind of similar to the ocular segregation concept that we actually showed here. But that was a pretty comprehensive paper. They have looked at different stuff in that work. It's very interesting study.
Yeah. One of the fundamental things that has never been resolved from experimental or computational neuroscience data or anything is, what is the purpose of ocular dominance columns? No, people used to think it's for binocular vision, but you can have binocular vision without ocular dominance columns. So it brings us back to why the segregation and what's its purpose. I mean, people still don't have an answer to that. It's 60 years on or 50 years on since. So we can explore this, I think, with VASO and BOLD and things like that. And these kinds of rivalry or perception or type of paradigms and so on, once you can robustly see this, which I think finally in 2023 or the 2020s, we're in a situation where we can do this.
Yeah.
I'm jealous of your coil. Guys, can we get one like this?
Yeah, well, sure. I mean, we do build coils occasionally for people, mostly collaborators,
Mhm.
or for people, you know, like MGH who just don't have the background. we actually have a spine. We have a spine PTX coil that we built for MGH, and one for Julian Cohen-Haddad in Montreal as well. And we've built some macaque coils and a few human coils. They're not super cheap, I have to warn you. They're not super expensive. NIH money grows on trees, so you don't care about that.
Oh yeah,
stuff.
that's
Yeah,
right.
but seriously, do you think you could have done this experiment with a head coil?
No.
No, it's not even. So I've tried with VASO to get 2 humps in V1, and I can't.
No, so our head coil, which is a 32 channel receive coil, 8 channel PTX, has about 2.4 times worse SNR than this coil.
And you're at the edge, basically.
And we're already at the edge, exactly. Yes.
So you are confirming that I cannot see this with equipment.
So I mean, you could do with a head coil. You just have to average, 12, 14 times longer, which is the problem.
How much average was this? How long were these scans?
These weren't long.
It was 5 runs, and each run took around 10, 11 minutes.
So it's an hour scanning, an hour and a half scan session.
Yeah.
So you don't think
it's on a bite bar or on a head case? How are they stabilized? No, just padded.
Just padded.
So you don't think Nordic would get us very far, getting rid of some of the thermal noise? I mean, it would reduce the differences between a good coil and a mediocre coil.
They're doing Nordic and they're at the edge.
And so you're doing Nordic, but maybe the benefits of Nordic are less because you already have high signal to noise, maybe, and then it would be more for us. Who knows? I don't know. I don't know.
Well, I mean, when we made the decision to build this coil, which was 3-4 years ago, at that point, Nordic wasn't out yet, but so that didn't enter into our approach. But there are actually some other very clever things using the phase that can be used for denoising as well. This probably won't come as much of a surprise to you, Peter, but others may not be so aware. So we're actually going to look at some of those as well, because you can actually use the phase maps to make maps as well, and you can throw the phase and the magnitude separately into a regression and look for similarities and things like that with math that's above my pay grade, but I have some smart people who can do this.
Have you looked without Nordic? I mean, how much does it actually help?
Well, that's a good question, Atena.
It actually helped a lot, especially for our phase regression study. For my case, it doubled the TSNR. Yeah, definitely. And I also, back into your previous question, back in Brisbane, we did VASO also in visual cortex with head coil, but we couldn't see this double peak pattern. And the number of averaging was kind of the same, if I'm not mistaken. I used to acquire 4 runs, probably 3 to 4 runs, and each run was 200 or 300 runs. And the TR back then was even longer.
Yeah, so this actually makes me feel a lot better because I have tried and failed.
No, I couldn't see it actually back in 2018, I guess. Yeah,
great. Or not to.
Yeah, I think, I mean, we always bring some kind of hardware solution to many of the things that we do, because they're always on the edge of where we want to be. So this coil wraps around quite a bit, And so it's designed to actually help with the immobilization, even without a bite bar and things like that. So I think that's helpful. Although Atena told me I was her best subject, so I don't know whether she's just buttering up her supervisor or whether I was actually her best subject.
No, you were really the best.
Because I can lie in a magnet and stare at blank screens for hours.
Honed over 30 years of
Yeah, exactly.
All right. Well, cool. This is great. Thank you. Thank
Yeah,
you.
really
Yeah, thanks
beautiful.
everybody for the feedback. That's
Yeah.
really helpful. I think you might want to make a few little tweaks to your paper, Atena, based on some of this. Really good. It's really enjoyable.
Yeah,
Yeah.
very much.
Well, you
Thank
should-
you so much, everyone.
Yeah, you're welcome to join us again.